The morning of March 10th, 1941, somewhere over New London, Connecticut, a Douglas B-18 Bolo bomber drone through overcast skies, its aging airframe shaking with each gust of wind. Inside the converted bomber's nose, physicist Edward Bowen hunched over a cathode ray tube no bigger than a dinner plate, watching a green blip pulse on the screen. Below, invisible through the clouds, a submarine sat on the surface. The radar had found it at nearly 5 miles. Nobody aboard the aircraft should have been able to see anything through the weather. Yet there it was, a solid return painting itself on the display, with each rotation of the parabolic dish mounted in the nose. What made this moment extraordinary was not that radar worked. British chain home stations had been detecting aircraft for years. What mattered was that this radar operated at 10 centimeters wavelength, used a spinning antenna that solved what British engineers had declared impossible, and weighed little enough to fit inside a fighter aircraft. The device that found that submarine would evolve into the SCR-720 radar, and that radar would transform a massive, ungainly aircraft called the P-61 Black Widow into the most effective night predator the skies had ever seen. The technology that made it possible came from one man's refusal to accept that a problem was unsolvable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Night had belonged to bombers since the war began. After September 1940, when Hermann Göring ordered the Luftwaffe to abandon daylight raids over Britain, the RAF's fighter pilots faced a brutal reality. The same Spitfires and Hurricanes that tore through bomber formations by day became nearly useless after sunset. A pilot might spot the faint blue exhaust flames of a Heinkel from a few hundred yards if the moon cooperated, but closing that distance before losing visual contact proved almost impossible. The bomber would simply vanish into darkness like a ghost melting through walls. The numbers told a grim story. During the night Blitz from September 1940 through May 1941, German bombers flew over 12,000 sorties against British cities. RAF night fighters managed to shoot down fewer than 75 of them, a success rate hovering around 0.5%. London, Coventry, Birmingham, Liverpool and Bristol burned while fighter pilots circled overhead in frustration, listening to the crump of explosions below but unable to locate the raiders dropping the bombs. The problem was not courage or skill, it was physics. Human eyes cannot scan enough sky fast enough to locate a target moving at 200 miles per hour through three-dimensional darkness. Detection range on even the brightest moonlit nights rarely exceeded 3 miles. Moonless nights reduced that to under 1,000 yards, and that assumed perfect weather, no haze, no clouds, no industrial smoke obscuring the target. Ground-based radar could track bomber formations, but talking a fighter into position proved maddeningly imprecise. Controllers watching primitive oscilloscopes could vector fighters to within perhaps 10 miles of an enemy formation, but 10 miles represented hundreds of cubic miles of empty sky. A fighter had to be within a few hundred yards to acquire a visual target at night. The gap between ground radar detection and visual acquisition was where missions died. British scientists had been experimenting with airborne radar since 1937, but the technology seemed impossibly complex. Early sets weighed over 1,000 pounds and required enormous antenna arrays that would turn any fighter into a lumbering pig. The wavelength had to be short enough to detect an aircraft-sized target, but long enough that the transmitter didn't require exotic components that couldn't be mass-produced. The receiver had to filter out ground clutter, ignore reflections from clouds, and present information on a display simple enough that an operator could interpret it while being thrown around in combat. The breakthrough came not from incremental improvement, but from revolutionary physics. In late 1939, British physicists at Birmingham University invented the cavity magnetron oscillator. This device, a copper cylinder with precision-machined cavities arranged around a central cathode, could generate enormous microwave power at frequencies 10 times higher than existing radar systems. Higher frequency meant shorter wavelength. Shorter wavelength meant smaller antennas and better resolution. Better resolution meant detecting smaller targets through ground clutter that blinded longer wavelength systems. The cavity magnetron was so revolutionary, so potentially war-winning, that Winston Churchill agonized over whether to share it with the Americans. If a magnetron fell into German hands through careless handling or enemy action, the Luftwaffe could copy the technology and regain the advantage Britain had sacrificed so much to achieve. But Britain stood alone in 1940. German invasion threatened daily. Churchill needed American industrial capacity and scientific expertise. The decision was made. Britain would share everything. The Tizard Mission arrived in Washington in September 1940, carrying secrets that would reshape the war. Among the documents and prototypes packed into what participants called the Black Box was cavity magnetron serial number 12. On September 19, 1940, in Alfred Loomis's apartment, British physicist Edward Bowen pulled the device from its case and demonstrated it to American researchers. The effect was electric. One US Navy representative had just finished explaining that American microwave research had reached a dead end, producing only tens of watts at 10 centimeter wavelength. Bowen's magnetron generated 10 kilowatts, 1,000 times more power. The Americans understood immediately that they were witnessing a leap forward in radar technology that peacetime research couldn't have achieved in decades. Alfred Loomis, millionaire physicist and head of the Microwave Committee within the National Defense Research Committee, moved quickly. Within weeks, he had established the Radiation Laboratory at the Massachusetts Institute of Technology. The RAD Lab, as it became known, opened officially in November 1940 with a single mission: turn the cavity magnetron into practical military radar systems before the war was lost. The RAD Lab organized into projects based on specific military needs. Project 1 focused on airborne interception radar, the system that would allow fighters to find bombers in darkness. Project 2 addressed gun-laying radar for anti-aircraft defense. Project 3 tackled long-range navigation. Each project pulled together the best physicists, engineers, and mathematicians America could muster. Many came from top universities. Some were Nobel laureates. Others were brilliant graduate students. All understood they were racing against time. Edwin Macmillan took charge of the engineering work for Project 1. At 33 years old, Macmillan was already an accomplished physicist. He'd earned his doctorate from Princeton, worked at the Berkeley Radiation Laboratory discovering new isotopes, and just months earlier had produced neptunium, the first transuranium element ever created. That work would eventually earn him the Nobel Prize in chemistry. But in 1941, Nobel Prizes seemed less urgent than preventing Nazi Germany from conquering Europe. Macmillan faced a problem that British engineers had struggled with for over a year. The radar needed to scan the sky ahead of the fighter, searching for targets across a wide field. This required moving the antenna. But how do you move a parabolic reflector while feeding it microwave energy from a magnetron? The frequencies involved, 3.3 GHz, could not be conducted through rotating joints or slip rings like lower-frequency radio waves. Microwave energy leaked from any imperfect connection. Losses became catastrophic. The British had abandoned the most elegant scanning solution, what they called helical scan, because they couldn't solve the feed problem. Helical scan worked like this. Mount the parabolic dish so it spins around a vertical axis while simultaneously tilting up and down. The radar beam sweeps across the sky in a corkscrew pattern, covering the entire search volume systematically. When the beam hits a target, the return echo spike appears on the display. The operator notes the bearing and elevation, calls corrections to the pilot, and the fighter turns to intercept. Simple in concept. Impossible in practice if you couldn't get power to the spinning antenna. British researchers had settled for an inferior solution. They mounted the dipole antenna on a fixed bracket facing forward and nutated the parabolic reflector behind it in small circles. This spiral scan worked, but the beam became increasingly defocused at greater angles from centerline. Detection range fell off dramatically when searching to the sides. It was a compromise born of engineering desperation. Macmillan refused to compromise. Through the winter of 1940–41, he worked with mechanical engineers and microwave specialists to solve the feed problem. The solution involved precision-machined waveguide sections and rotary joints that maintained microwave coupling despite continuous rotation. It required tolerances measured in thousandths of an inch. Any misalignment caused losses that killed performance, but by March 1941, they had it working. The first flight test occurred on March 10, 1941, aboard that Douglas B-18 Bolo. The radar detected targets at ranges, approaching 10 miles. Ground clutter, the curse of longer wavelength systems, barely registered. The microwave frequencies allowed the narrow beam to distinguish between aircraft and the ground below. When Bowen flew the test profile past New London, the system detected a surfaced submarine at 4 to 5 miles. No visual sighting was needed. The radar simply painted the target on the scope. Hugh Dowding, architect of Britain's air defence during the Battle of Britain, happened to be visiting the United States at the time. When he learned of the test results, he demanded to see the system for himself. On April 29th, after detecting a target aircraft at 2 to 3 miles, Dowding asked about minimum range. They demonstrated that the radar could track targets down to 500 feet. Dowding understood immediately what this meant. A night fighter equipped with this radar could search an enormous volume of sky, detect targets at useful ranges, and close to visual identification distance before the bomber crew knew they were being hunted. The radar was designated SCR 520, Signal Corps Radio, Model 520. It represented America's first operational microwave radar, but it was too heavy for fighter installation. The complete system weighed 600 pounds spread across 12 units. The largest components measured roughly 1 yard cubed. Only the biggest aircraft could accommodate that bulk. The Douglas P-70, a converted A-20 Havoc bomber, could carry it, but the P-70 lacked the performance to catch many German bombers. What the Army Air Forces needed was a purpose-designed night fighter built from the start to carry advanced radar. An aircraft large enough for a 3-man crew, pilot, gunner and radar operator, fast enough to overtake bombers, maneuverable enough to dogfight if necessary, armed heavily enough to destroy targets with short bursts, and equipped with radar sophisticated enough to find targets in any weather, at night, through clouds or industrial haze. Northrop Corporation proposed exactly that aircraft in January 1941. Jack Northrop, the brilliant aerospace engineer who had already designed innovative aircraft like the Flying Wing prototypes, submitted plans for a twin-engine, twin-boom night fighter. The central nacelle would house the 3-man crew, radar, and weapons. Engines mounted in outboard booms would drive counter-rotating propellers for stability. A twin-tail configuration would provide control in the turbulent air behind enemy bombers. The design was radical, expensive, and exactly what the situation demanded. The Army Air Corps awarded Northrop a development contract on January 13, 1941. The specifications called for maximum speed over 360 miles per hour, service ceiling above 30,000 feet, range exceeding 1,000 miles, and armament heavy enough to destroy bombers quickly. Most critically, the aircraft had to accommodate the SCR radar system that Macmillan's team was developing. Everything else about the design served that central requirement. Northrop's engineers worked in parallel with the RAD lab. As Macmillan refined the SCR 520 through 1941 and into 1942, Northrop modified the prototype night fighter's nose to accept the rotating parabolic dish and associated electronics. The radar operator's position had to provide access to 2 separate cathode ray tubes, one showing azimuth, one showing elevation. The operator needed to correlate information from both displays while calling steering corrections to the pilot, all while fighting air sickness in a blacked-out fuselage being thrown around by turbulence and combat maneuvers. By late 1942, Western Electric had taken over production engineering for what was now designated SCR 720. The redesign reduced weight to 412 pounds, down from 600. More importantly, the system became dramatically more reliable. Early SCR 520 units failed on roughly half of all sorties. Vacuum tubes burned out from vibration. Connections worked loose during high-G maneuvers. Moisture seeped into junction boxes and caused shorts. The SCR 720 addressed these problems through better packaging, vibration-resistant tube sockets, and hermetically sealed components. The radar operated at 3.3 GHz frequency, producing 9.1 centimeter wavelength. Peak power output reached 40 kilowatts per pulse. The helical scan antenna swept a 180-degree arc ahead of the aircraft, searching from horizon to horizon. Altitude coverage could be selected for different threat profiles: 0 to 0 degrees for level search, -5 to +5 degrees for shallow climbs or descents, +5 to +20 degrees for targets climbing away, +20 to +50 degrees for high-altitude intercepting. Detection range varied with target size and atmospheric conditions, but typical performance against bomber-sized targets reached 4 to 5 miles. The minimum range, limited by the time it took for transmitted pulses to clear the receiver before return echoes arrived, was about 400 feet. This meant the radar operator would guide the pilot to within visual range, roughly 1,000 yards. Then the pilot would complete the intercept visually. The radar couldn't be used for the final gun-firing solution, but it could put a fighter within gun range of a target that neither crew member could see with their eyes. The system included IFF, identification friend or foe, to prevent shooting down Allied aircraft. The operator could query suspicious contacts. Friendly aircraft would respond with coded pulses. Lack of response indicated enemy aircraft or friendly aircraft with malfunctioning IFF. Either way, the operator proceeded with caution, closing for visual identification before opening fire. Night combat was prone to deadly misunderstandings. More than one Allied aircraft had been shot down by friendly fighters who misidentified silhouettes in darkness. Multiple cathode ray tube displays gave the SCR-720 substantial resistance to chaff, the aluminum foil strips that bombers would later drop to create false radar returns. The operator could switch range scales, changing from 1 mile to 10 miles to 20 miles to 100 miles depending on the tactical situation. Wide-scale settings helped detect formations at long range. Narrow-scale settings helped track individual bombers through chaff clouds. The flexibility proved decisive when both sides began electronic warfare tactics. While Macmillan's team perfected the radar through 1941 and 42, Northrop's engineers wrestled with the massive airframe that would carry it. The P-61 prototype was enormous by fighter standards. Wingspan 66 feet, length 49 feet, height over 14 feet, empty weight approaching 21,000 pounds. This was larger than many medium bombers. Critics wondered whether such a huge aircraft could maneuver well enough for fighter combat. Vance Breeze, Northrop's senior test pilot, took the P-61 prototype aloft for the first time on May 26, 1942. After landing, he told Jack Northrop directly, "Jack, you've got a damn fine airplane." The Black Widow, as it was now being called, handled far better than its size suggested. The twin-boom configuration provided excellent stability. Spoilers rather than ailerons gave crisp roll response without adverse yaw. The Pratt & Whitney R2800 double Wasp engines, each producing 2,000 horsepower, provided acceleration that shocked pilots transitioning from smaller fighters. But the radar wasn't ready. The P-61 prototype flew without radar, carrying ballast in its place. Some early YP-61 service test aircraft received the old SCR-520 for evaluation. The installation revealed problems. The electronics boxes overheated. The rotating antenna created vibrations that propagated through the airframe. Ground clutter still caused false returns when searching for low-altitude targets. The RAD Lab and Western Electric continued refining the system through 1942 and into 1943. Production P-61. Models began rolling off Northrop's assembly lines in October 1943. These aircraft carried the definitive SCR-720C radar. The system now worked reliably in combat conditions. Maximum detection range against bomber-sized targets reached 5 miles under good conditions. 4 miles was typical. 3 miles was guaranteed unless the target was deliberately maneuvering to break lock. Minimum range remained 400 feet, still short enough for most intercept profiles. The first operational Black Widow unit, the 348th Night Fighter Squadron at Orlando Army Air Base, Florida, began receiving aircraft in late 1943. The squadron's job was training, not combat. Crews learning to operate this complex aircraft needed months of practice before deployment. Pilots had to master the peculiar flight characteristics. Gunners had to learn the remote-controlled turret system that allowed them to engage targets behind the aircraft. Radar operators needed to become fluent in reading two-dimensional cathode ray displays and translating blips into three-dimensional intercept geometry. The radar operator's job was the most complex. He sat in near-total darkness, hunched over glowing green screens, watching abstract representations of aircraft positions. The azimuth scope showed left-right bearing. The elevation scope showed up-down angle. Range appeared as the distance of the blip from the center of the display. As the target moved, the blip moved. As the Black Widow maneuvered, the blip's position changed relative to the fine-roading aircraft's heading. The operator had to maintain three-dimensional situational awareness, using two-dimensional displays that showed only abstractions. Training emphasized smooth, calm communication under stress. Contact, 3 o'clock, 4 miles, slightly high. The pilot would turn right and climb gently while the operator refined the geometry. Contact moving left, range closing, 3 miles. The pilot would adjust heading. 2 miles, dead ahead, level now. The pilot would fine-tune his flight path, easing the Black Widow into position behind the target. 1 mile, still dead ahead. Both crewmen would strain their eyes, searching the darkness ahead for any visual sign of the bomber they were stalking. Often, the first visual acquisition came at less than 1,000 yards. The operator would lose the contact below minimum radar range, and for a few heartbeats the crew would fly blind, holding course and speed, trusting their intercept geometry was correct. Then, suddenly, a dark shape would appear against slightly less dark sky, or exhaust flames from the target's engines would glow faint blue, or moonlight would catch a wing surface for an instant. Visual contact. The pilot would close carefully, confirming the target's identity before firing. 4 20mm cannon would then shred the bomber in seconds, a devastating burst of fire that few aircraft could survive. The Black Widows began deploying overseas in March 1944. The 422nd Night Fighter Squadron received the first P-61 aircraft in England in May 1944. Training and shakedown flights consumed several weeks. The crews were volunteers, every one of them. Night fighting required courage that exceeded what any pilot had needed before. You hunted blind, trusting technology most people didn't understand. You closed on targets you couldn't see, guided by a radar operator reading abstract displays. You fought alone in darkness where disorientation killed as surely as enemy fire. And you did it knowing that if anything went wrong, engine failure, combat damage, fuel exhaustion, your chances of survival were minimal. Night bailouts in combat conditions rarely ended well. Combat operations began in earnest after D-Day. June 6, 1944, Black Widows flew deep into German airspace, hunting for Luftwaffe night fighters that were attacking Allied bomber streams. The Germans had their own radar-equipped night fighters, Messerschmitt Bf-110 and Junkers Ju-88 aircraft carrying Liechtenstein radar. These aircraft had savaged RAF Bomber Command through 1943, shooting down thousands of British bombers. Now the Black Widows turned the tables, hunting the hunters. The P-61s also flew intruder missions, prowling German airspace to attack trains, convoys, and aircraft on the ground. The 20mm cannon proved devastatingly effective against locomotives and trucks. Pilots would spot targets using their radar, then close visually and strafe. The black paint scheme, scientifically determined by MIT researchers to be the least visible color at night, made the Black Widows nearly impossible to spot from the ground. Searchlights rarely found them. Anti-aircraft fire proved largely ineffective against targets moving unpredictably through darkness. In the Pacific Theater, Black Widows began operations in early June 1944. The 6th Night Fighter Squadron on Guadalcanal received the first aircraft. These were assembled quickly, flight-tested, and declared operational by late June. Japanese bombers had been conducting nuisance raids against American installations for years, operating at night when Allied fighters couldn't intercept them effectively. The arrival of radar-equipped night fighters changed that equation instantly. On June 30, 1944, a P-61 from the 6th Night Fighter Squadron intercepted a Mitsubishi G-4M Betty bomber returning from a raid. The Black Widow's radar detected the bomber at roughly 4 miles. The crew closed smoothly, acquired visual contact at about 800 yards, confirmed the target was enemy, and opened fire. The Betty exploded, becoming the first confirmed kill for the P-61 Black Widow. More would follow quickly. Japanese night raiders increasingly failed to return home. The Black Widows owned the night skies. If they could detect a target, they could usually kill it. The radar gave them enormous tactical advantage. Japanese crews had no warning of interception until cannon shells started hitting their aircraft. By the time they saw muzzle flashes or felt impacts, it was usually too late to evade. The Black Widow could maintain position in total darkness, tracking targets through turns and climbs, waiting for the perfect firing solution before unleashing a devastating burst. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The effectiveness of the SCR-720 radar extended beyond simple target detection. The system's multiple display modes and range scales allowed operators to develop sophisticated search patterns. They could sweep wide areas at maximum range, detecting formations. Once contact was established, they could zoom in for precise tracking. They could distinguish between individual aircraft in a formation, selecting the most vulnerable target. They could maintain lock through evasive maneuvers that would have broken visual contact instantly. The helical scan pattern that Macmillan had worked so hard to perfect proved essential. The systematic coverage ensured that targets anywhere in the search volume would eventually appear on the scope. Unlike spiral scan, which lost effectiveness toward the edges of the search pattern, helical scan maintained good detection throughout the sweep. This meant fewer missed contacts and higher interception rates. German and Japanese intelligence officers struggled to understand how Allied night fighters had become so effective. Luftwaffe bomber crews reported attacks from impossible angles, suggesting the fighters could somehow see in complete darkness. Japanese pilots described being intercepted miles from their targets, before anti-aircraft fire could alert defenders to their approach. Both Axis powers suspected radar, but didn't understand the sophistication of Allied systems. The Germans had developed their own cavity magnetrons following capture of British H-2S bombing radar in early 1943. They understood microwave radar conceptually, but German industrial capacity, already strained by Allied bombing and material shortages, couldn't match Allied radar production. German night fighters carried centimetric radar by late war, but in numbers too small to affect the strategic balance. More critically, German radar development focused on defensive systems, protecting the homeland from bomber streams. Offensive radar for intruder operations received lower priority. Japanese radar development lagged even further behind. Japan lacked the industrial base and scientific infrastructure to develop sophisticated microwave systems. Japanese night fighters relied primarily on visual detection, aided by searchlights and ground-based radar vectoring. When they encountered radar-equipped American night fighters, the technological gap was insurmountable. Japanese crews died without understanding what had killed them. Throughout late 1944 and into 1945, Black Widow squadrons accumulated impressive kill tallies. The aircraft destroyed 127 enemy aircraft confirmed, including 18 German Von Buzz bombs. In the European theatre, 53 manned aircraft and 9 V-1s. In the Mediterranean theatre, 5 manned aircraft. In the Pacific theatre, 64 manned aircraft. In the China, Burma, India theatre, 5 more aircraft. These numbers represented not just destroyed machines, but confirmed proof that radar-guided night interception worked. 3 Black Widow crews became aces, credited with 5 or more kills. In the European theatre, pilot Hermann Ernst and radar operator Edward Bowen scored 6 kills, including a Von. Pilot Paul Smith and radar operator Robert Tierney also scored 6 kills, including a Von. In the Pacific Theater, pilot Carol Smith and radar operator Philip Porter scored 5 kills. Every victory validated the technology that Macmillan and his team had developed under pressure at the RAD lab. The SCR-720's immunity to chaff proved particularly valuable in later war operations. By mid-1944, both sides were dropping massive quantities of aluminum foil strips to blind enemy radar. German formations dropped chaff to confuse Allied gun-laying radar and night fighter intercepts. Allied bombers dropped window, as the British called it, to saturate German defensive radar. In this electronic warfare environment, the SCR-720's multiple range scales and display modes allowed operators to discriminate real targets from false returns. The technique required skill and experience. The operator would set the radar to maximum range, detecting targets before they entered heavy chaff concentrations. Once contact was established, he would carefully adjust range scales, tracking the target while allowing chaff to scroll off the display edge. Real aircraft maintained steady bearing while chaff bloomed and dispersed. By switching between range settings and display modes, skilled operators could maintain lock-through chaff that completely blinded simpler radar systems. British operators flying de Havilland Mosquito night fighters with AI Mark 10 radar, the British production version of the SCR-720, reported similar success against chaff. Post-war surveys found that using the SCR-720 made it significantly harder to lose maneuvering targets compared to earlier radar sets. The range azimuth display allowed operators to follow target course changes intuitively. The wide vertical coverage meant rapidly descending targets were unlikely to drop below the radar's search volume. The system made intercepts easier even when targets were crossing the night fighter's flight path at high angles. However, the SCR-720 was not without limitations. The system was mechanically complex, requiring careful maintenance. Ground crews needed specialized training just to troubleshoot the black boxes that made up the radar. The rotating antenna assembly required precise alignment. Any wobble or imbalance created vibrations that could damage delicate microwave components. The vacuum tubes that powered the system remained fragile despite improvements. Rough landings could shake tubes loose from their sockets. High-G maneuvers sometimes caused temporary malfunctions. The pressurized containers that held many vital components had a tendency to depressurize at altitude, especially in tropical heat. Electrical arcing would disable the entire system. The 419 Night Fighter Squadron in the Pacific developed an improvised fix using engine-driven vacuum pumps to maintain pressure. It's unknown whether other squadrons adopted this modification. Early P-61 models with plastic radomes encountered problems in tropical Sunday. The nose would soften and deform, affecting radar performance until metal radomes replaced the plastic versions. Despite these teething troubles, the Black Widow proved itself as an outstanding night fighter. Pilots praised its handling characteristics. Squadron leader Frederick Jenks, a production project engineer who flew the aircraft extensively, wrote that the P-61 was an honest airplane with no mean tricks. It performed aerobatics like loops, spins, Immelmans, and fast turns as smoothly as any pursuit plane should. Its stalling behavior was near perfect. This was remarkable for an aircraft weighing over 30,000 pounds fully loaded. The Black Widow's armament made it lethal once it achieved firing position. 4 20mm Hispano M2 cannon mounted in the lower fuselage fired directly ahead with convergent fire paths. This arrangement, with guns clustered tightly together, proved superior to wing-mounted guns that required convergent settings. Every shell travelled nearly the same trajectory. When the guns were on target, they were all on target. 200 rounds per gun provided 40 seconds of firing time if used continuously. In practice, pilots fired short bursts of 1 or 2 seconds. This gave them 20 to 40 distinct firing opportunities before ammunition was exhausted. The dorsal turret carried 450 caliber Browning M2 machine guns, each with 500 rounds. The turret could rotate through 360 degrees and elevate to 90 degrees above the aircraft. Any crew member could control it. The gunner could engage targets behind or above the Black Widow, while the pilot focused on flying. The radar operator could use it against targets that appeared unexpectedly during approaches. The pilot could lock it forward to provide additional firepower during frontal attacks. This flexibility proved valuable in the chaotic geometry of night combat, where threats could appear from unexpected angles. Some early P-61 models lacked the turret due to production difficulties. General Electric struggled to manufacture the remote control system in sufficient quantities. Aircraft delivered without turrets carried ballast to maintain proper center of gravity. Later, P-61B models reintroduced the turret after buffeting problems were resolved. Still later, P-61B subvariants included improved turret designs that reduced vibration and mechanical complexity. The aircraft could also carry external stores: 4 underwing hardpoints, 2 inboard and 2 outboard of each engine boom, could mount drop tanks for extended range or bombs for ground attack missions. The external tanks were wet, meaning they connected to the aircraft's fuel system. This extended combat radius from approximately 600 miles to over 900 miles, allowing Black Widows to patrol deeper into enemy territory or loiter longer over potential intercept zones. 8 stub pylons under the outer wings could carry 5-inch high-velocity aircraft rockets. These proved effective against ground targets like locomotives, trucks, and buildings. Some crews used rockets against ships in harbour, attacking from darkness before defences could respond. The rocket launchers were rarely installed on aircraft assigned pure night fighter missions, as the drag reduced performance. But for intruder and ground attack operations, the additional firepower proved valuable. The technological advantage that Edwin Macmillan's helical scan innovation provided went beyond mere detection capability. It represented a fundamental shift in the nature of aerial combat. For the first time in aviation history, darkness no longer protected attackers. The night, which had been a cloak that made bombers nearly invulnerable, became a hunting ground where radar-equipped fighters held every advantage. Japanese bomber crews operating over the Pacific discovered this reality with brutal finality in the summer of 1944. On the night of July 7, 1944, pilot Dale Huberman and radar operator Ray Mooney were flying a P-61 named Moon Happy on patrol near their base. Ground controllers vectored them toward an incoming contact. The radar painted a clear return at roughly 4 miles. As they closed, a second blip appeared on the scope. What ground radar had seen as a single aircraft was actually 2. A Mitsubishi Zero fighter was tucked so tightly under the wing of a Betty bomber that their radar cross-sections had merged. Huberman allowed the formation to pass overhead, then used the Black Widow's spoilerons to execute a sharp 180-degree turn, climbing to 17,000 feet. The Japanese crews had no idea they were being followed. The Black Widow was virtually invisible at night, painted glossy black with no navigation lights. Huberman positioned himself carefully behind the formation, maintaining range while Mooney tracked both targets on his scope. The geometry was tricky. Firing too close risked debris from the bomber damaging the Black Widow. Firing at the wrong angle might hit the Zero first, alerting the Betty crew and giving them a chance to evade. Huberman chose his moment carefully. A short burst from the 420mm cannon struck the Betty's wing, root, and fuselage. Fuel tanks exploded. The bomber rolled inverted and plunged toward the ocean, burning. The Zero pilot, shocked by the sudden destruction of his charge, broke hard left and dove. But Mooney had maintained radar lock on both targets. Huberman followed the dive, closed to firing range, and destroyed the Zero with another precise burst. 2 kills in less than 3 minutes, neither target aware of the Black Widow's presence until cannon shells were already hitting them. This was not luck. This was the operational reality that Macmillan's radar created. A night fighter crew could detect, track, and engage multiple targets in conditions where visual detection was impossible. The helical scan antenna swept continuously, maintaining awareness of the tactical situation even during evasive maneuvers. The radar operator could monitor the entire forward hemisphere, alerting the pilot to threats or opportunities that appeared anywhere in the search volume. The pilot could focus on flying and weapons employment, trusting the operator to provide accurate intercept geometry. The psychological impact on enemy bomber crews was profound. German and Japanese airmen had grown accustomed to operating with to the safe, near impunity at night. Anti-aircraft fire was predictable, easily avoided with altitude changes and course corrections. Searchlights were slow and could be outmaneuvered. The occasional night fighter encounter usually ended with the bomber escaping into darkness, but radar-equipped Allied night fighters changed everything. Bombers could be intercepted far from their targets, attacked from positions that should have been impossible, destroyed before crews understood they were in danger. Luftwaffe intelligence reports from late 1944 described increasing reluctance among bomber crews to fly night missions over Allied-controlled territory. The odds of returning had shifted dramatically. In early 1943, before widespread deployment of centimetric radar, German bomber crews faced roughly 1% loss rates on night missions. By late 1944, after Black Widows and radar-equipped Mosquitoes were operating in numbers, loss rates on some missions approached 10%. No air force could sustain such casualties for extended periods. The SCR-720's success prompted both admiration and desperate countermeasures. German radar warning receivers, initially designed to detect meter-wavelength British AI Mark IV radar, were useless against centimetric frequencies. The Naxos system, introduced in September 1943, could detect some Allied microwave emissions, but by the time Naxos reached operational squadrons, it was already obsolete. American and British scientists had developed 3-centimeter radar systems that operated at frequencies Naxos couldn't detect. The Allies remained perpetually one generation ahead, forever rendering German countermeasures insufficient before they could be widely deployed. Japanese efforts lagged even further. Japan captured SCR-720 components from downed aircraft, but lacked the industrial infrastructure to reverse engineer and produce copies. Japanese magnetrons remained inferior in power output and reliability. Japanese radar operators worked with equipment that German engineers would have rejected as inadequate. When Japanese night fighters encountered P-61 Black Widows, the outcome was rarely in doubt. American radar detected Japanese aircraft long before Japanese crews knew American fighters were nearby. American cannon outranged Japanese weapons. American pilots had better training and more combat experience. The technological advantage simply amplified existing Allied superiority. The European theatre presented different challenges. By late 1944, the Luftwaffe was running desperately short of aviation fuel. German fighters increasingly spent their time on the ground, grounded by fuel shortages rather than Allied air superiority. Black Widow crews found fewer aerial targets as 1944 turned to 1945, so they adapted their tactics, transitioning from pure night fighter operations to intruder missions deep in German airspace. P-61 crews would penetrate German territory after dark, using their radar to navigate and locate targets. Trains became priority objectives. German logistics depended on rail transport, moving troops, ammunition, and supplies to frontline units under cover of darkness to avoid Allied fighter bombers. Black Widow crews would detect trains from miles away, the metal locomotives and rail cars producing excellent radar returns. They would close to visual range, identify the target, then attack with cannon fire. A 2-second burst from 4 20mm cannon could wreck a locomotive, immobilizing an entire train. Road convoys provided additional targets. German trucks and half-tracks produced smaller radar returns than locomotives, but they were still detectable at a mile or more in open terrain. Crews learned to distinguish between friendly and enemy vehicles by their locations and movement patterns. Anything moving on roads in German territory after dark was legitimate target. The Black Widows would orbit at altitude, searching with radar, then dive to strafe when targets appeared. The attacks were devastating. Drivers had no warning until cannon shells began ripping through vehicles. Convoys would scatter, abandoning trucks and equipment, fleeing into darkness on foot. The Battle of the Bulge, in December 1944, saw intensive Black Widow operations. German forces launched their surprise offensive through the Ardennes in terrible weather that grounded most Allied aircraft, but Black Widows could operate in weather that kept other aircraft on the ground. Their radar allowed navigation through clouds and storms that would have defeated visual navigation. P-61 crews flew patrol after patrol, hunting for German reinforcement columns moving toward the fighting. They couldn't stop the offensive alone, but they inflicted steady attrition on German logistics and morale. One crew from the 422nd Night Fighter Squadron intercepted and destroyed a Junkers Ju-88 bomber that was attacking Allied positions. The German aircraft was operating at low altitude in heavy clouds, conditions where visual detection was impossible. The Black Widow's radar found it anyway. The crew closed through solid overcast, acquired visual contact only when they were within 400 yards, and destroyed the bomber with a single burst. The Ju-88 crashed in German-held territory. The entire intercept, from initial detection to confirmed kill, took less than 5 minutes and occurred entirely inside clouds, where neither crew could see the ground or horizon. The Black Widow's all-weather capability proved equally valuable in the Pacific. Tropical weather patterns created sudden squalls and heavy rain that reduced visibility to zero. Japanese aircraft sometimes used these conditions to escape pursuit or approach targets undetected. But the SCR-720 could see through weather that blinded human eyes. Heavy rain did create clutter on the radar display, but skilled operators learned to distinguish real targets from precipitation returns. Aircraft produced steady echoes that moved predictably. Rain produced fuzzy, dispersed returns that shifted with wind patterns. By early 1945, Black Widow crews had refined their tactics to near perfection. Standard intercept procedures began with ground controllers vectoring the fighter to within 10 miles of the target using ground-based radar. The Black Widow's radar operator would then search the directed sector, sweeping systematically until contact appeared on his scope. Once he acquired the target, he would call range, bearing, and altitude to the pilot, who would begin a gentle intercept curve designed to position the Black Widow behind and slightly below the target. The approach had to be smooth. Sudden maneuvers would alert experienced bomber crews that they were being stalked, but a careful, steady closure looked like random patrol movements on the bomber's radar, if the bomber even had radar. Most Japanese aircraft didn't. German bombers carried radar warning receivers, but steady closure from behind often didn't trigger alarms that were calibrated to detect search radar painting them from multiple directions. The Black Widow would creep closer, 4 miles to 3 miles to 2 miles, while the operator refined tracking and called corrections. At 1 mile, visual acquisition became critical. The radar's minimum range limitation meant the operator would lose contact before the pilot reached gun range. This was the moment of maximum vulnerability. If visual acquisition failed, the intercept failed. Crews would have to break off, reacquire radar contact, and attempt another approach. But experienced crews developed techniques for maximizing visual acquisition odds. They would position themselves slightly below and behind the target, looking for the bomber's silhouette against stars or clouds. They would watch for engine exhaust flames, faint blue glows that were invisible at longer ranges but became visible inside 1,000 yards. They would use moonlight when available, timing approaches so the target appeared against brighter portions of the sky. Once visual contact was confirmed, the pilot would close to between 400 and 600 yards. This was the optimal firing range. Close enough for accurate shooting, far enough to avoid debris if the target exploded. The pilot would center the target in his gun sight, a lighted reticle calibrated for the cannon's ballistic trajectory. Then he would fire a 2 to 3 second burst. 4 20mm cannon, each firing at roughly 600 rounds per minute, would send 80 to 120 high-explosive shells into the target in that brief moment. The result was usually catastrophic. Bomber wings contained fuel tanks, fuselages held bombs or ammunition, engines were filled with flammable fluids. A single high-explosive shell hitting a fuel tank could rupture it, spraying fuel that ignited from engine heat or electrical sparks. Multiple shells hitting simultaneously would tear through aluminum skin, shred hydraulic lines, sever control cables, and ignite fires in multiple locations. Most bombers caught by a well-executed attack simply exploded or disintegrated. Crew survival rates were minimal. The attack happened so quickly that bomber crews rarely had time to bail out, even if they realized they were under attack. The lethality of radar-guided night attacks troubled some Allied airmen. Shooting down an enemy bomber in daylight gave the crew a chance to see the fighter, attempt evasion, return fire, and possibly bail out if their aircraft was disabled. Night attacks guided by radar gave bomber crews none of these chances. They died without warning, without opportunity to defend themselves, without time to escape. It was efficient. It was effective. It was also deeply impersonal in a way that traditional air combat was not. Flight Sergeant Robert Braun, a radar operator aboard a Lancaster bomber from 576 Squadron, experienced this from the receiving end on the night of February 19, 1944. His aircraft was one of 823 bombers attacking Leipzig. The first indication of attack came when 20mm shells punched through the floor beneath his feet and detonated in the fuselage above. This was Schrager Musik, upward-firing cannon installed in German night fighters using tactics similar to American and British radar intercepts. The Lancaster shuddered. Flames erupted from the port wing. The pilot screamed for everyone to bail out. Braun tumbled through the escape hatch into freezing darkness, pulled his ripcord, and watched his Lancaster spiral downward, trailing fire. 4 of his crew died in the aircraft. He never learned what killed them because there was nothing to see, just sudden fire from below and death arriving without warning. The technological arms race continued accelerating through 1945. Western Electric developed the SCR-720B, an improved version with better jamming resistance and longer detection range. The British adopted it as AI Mark 10, installing it in Mosquito night fighters. Post-war assessments found that AI Mark 10 equipped Mosquitoes were responsible for shooting down significant numbers of German aircraft in the final months of the war. The radar's ability to track maneuvering targets through chaff gave British crews decisive advantages in the electronic warfare environment that characterized late-war operations. The US Navy showed interest in the SCR-720 for shipboard applications. Several Essex-class aircraft carriers were fitted with SCR-720 units mounted on their catwalks. These installations covered the blind spot directly overhead that conventional naval radar couldn't reach. Ships' radar could search to roughly 75 degrees above the horizon, but no higher. This created a conical blind zone directly overhead. Japanese kamikaze pilots had learned to exploit this blind spot, approaching targets from high altitude, then diving nearly vertically. The SCR-720 could search to 90 degrees elevation, covering the entire upper hemisphere. This gave carriers warning of attacks that traditional radar would miss entirely. The P-61 itself evolved through 1944 and 45. The P-61B, introduced in mid-1944, featured the improved SCR-720C radar, with extended nose section, mechanically operated landing gear doors that reduced failures, improved crew heating, and automatically actuated cowl flaps. These refinements addressed problems discovered during combat operations. The P-61C, introduced in July 1945, featured turbocharged R2873 engines, producing 2,800 horsepower each, providing significantly better performance at altitude. Top speed increased to over 400 miles per hour. Service ceiling climbed above 40,000 feet. But the war ended before the C model saw combat. Total P-61 production reached 706 aircraft, including 36 15 reconnaissance variants. This was far fewer than other fighter types. The P-51 Mustang, for comparison, saw over 15,000 produced. But the Black Widow filled a specialized role that required relatively few aircraft. Night fighter squadrons typically operated with 12 to 16 aircraft, 8 squadrons in the Pacific Theater, 2 in the European Theater, a handful in the Mediterranean and China-Burma India. Total requirement never exceeded 200 aircraft in combat zones at any given time. The remainder supported training, replacement, and stateside air defense. The final aerial victory of World War II belonged to a P-61. On the night of August 14th to 15th, 1945, P-61, B-2, serial number 42 to 39408, named Lady in the Dark by her crew, was flying patrol near Shima. Japan had announced surrender, but formal cessation of hostilities had not yet occurred. Nobody was certain whether all Japanese units had received the surrender order. American commanders ordered defensive patrols to continue. Lieutenant Lee Kendall piloting and Lieutenant John Shearer operating radar detected a contact approaching at high speed. The radar painted a clear return at approximately 5 miles. They closed for interception. At roughly 2,000 yards, Kendall acquired visual contact. The target was a Nakajima Ki-44 Tojo fighter, apparently unaware of the surrender or choosing to ignore it. Kendall positioned Lady in the Dark behind and slightly below the Japanese fighter. Before he could fire, the Tojo pilot spotted the Black Widow and reacted violently, diving to wave-top altitude and beginning extreme evasive maneuvers. Kendall followed, maintaining position using radar guidance when visual contact was lost during hard turns. Shearer called corrections, keeping Kendall pointed at the target despite the wild maneuvering. The chase continued at extremely low altitude, both aircraft pulling maximum G-forces, engines at maximum power. Then the Tojo pilot made a fatal error. Pulling too hard in a desperate evasion attempt, he lost altitude control. The fighter struck the water at high speed and exploded. Lady in the Dark hadn't fired a shot, but she was credited with the kill. The Tojo had destroyed itself, attempting to evade a radar-guided opponent it couldn't shake. The war officially ended on August 15, 1945. But American commanders weren't certain all Japanese units had received the surrender message. Defensive patrols continued through the night of August 15th to 16th. Lady in the Dark flew again. Kendall and Shearer detected an incoming aircraft. Again, they closed for interception. Again, they engaged a Japanese fighter, this time identified as a Ki-43 Oscar. The engagement mirrored the previous night. Visual contact, aggressive evasion by the Japanese pilot, a low-altitude chase where radar guidance proved decisive. This time, the Oscar didn't crash. It simply disappeared into darkness. Ground troops found the wreckage the next day. Whether it crashed attempting evasion or was shot down remains unclear in historical records. What is clear is that Edwin Macmillan's solution to the helical scan problem, developed under pressure at the MIT Radiation Laboratory in early 1941, fundamentally changed aerial warfare. The technology that first flew in a Douglas B-18 Bolo over Connecticut in March 1941 matured into operational systems that destroyed over 100 enemy aircraft and demonstrated that night no longer protected attackers from detection and engagement. The SCR-720 represented more than incremental improvement over existing radar. It was a revolutionary leap that established patterns for airborne radar development that persisted for decades. The helical scan search mode combined with precision tracking, the multiple display modes providing different information for search versus track, the integration with ground-based radar for vectoring to initial contact. These concepts, refined under wartime pressure, became standard features of post-war radar systems. The MIT Radiation Laboratory closed on December 31, 1945. Its mission complete, the thousands of scientists and engineers who had worked there dispersed to universities, industry, and new laboratories. But their legacy extended far beyond the war. Technologies developed at the RAD Lab became foundations for post-war communications, navigation, and sensor systems. The SCR-584 gun-laying radar influenced anti-aircraft systems for decades. The H-2X bombing radar evolved into weather radar that saved countless lives by allowing aircraft to detect and avoid dangerous storms. LORAN navigation, developed at the RAD Lab, provided global navigation capability until GPS replaced it in the 1990s. And the SCR-720, Macmillan's solution to what British engineers had declared an impossible problem, remained in service long after World War II ended. The British Royal Air Force continued using AI Mark 10, their version of the SCR-720, well into the 1950s. The de Havilland Sea Vixen, the last aircraft equipped with AI Mark 10, remained in second-line roles until 1970. 25 years after Macmillan's first successful flight test, his helical scan radar was still guiding fighters to targets in darkness. Edwin Macmillan returned to Berkeley after the war, resuming his physics research. He shared the 1951 Nobel Prize in Chemistry with Glenn Seaborg for their work on transuranium elements. He directed the Lawrence Berkeley National Laboratory for many years, overseeing research that advanced nuclear physics, particle physics, and accelerator design. He passed away on September 7, 1991, at age 83. Obituaries focused primarily on his Nobel Prize-winning work and his contributions to nuclear physics. His wartime radar development rarely appeared in biographical summaries. But for the bomber crews who died without warning over Germany and the Pacific, shot down by fighters guided by radar they couldn't detect, Macmillan's contribution to the war was arguably more immediately consequential than his Nobel Prize work. The helical scan solution he developed allowed systematic coverage of the entire forward hemisphere, ensuring targets anywhere in the search volume would be detected. That innovation, combined with the cavity magnetron's microwave power, created the technological foundation for effective radar-guided night fighting. The P-61 Black Widow serves today as museum pieces, carefully preserved examples of wartime technology. The Smithsonian's National Air and Space Museum displays P-61C serial number 43 to 8330 at the Udvar Hazy Center. This particular aircraft was delivered in July 1945, too late to see combat. It participated in cold weather tests in Alaska, then joined the National Thunderstorm Project, studying storm systems and helping develop knowledge that improved aviation safety. In 1951, the aircraft was loaned to NACA for high-altitude drop tests of swept-wing aerodynamic drones. It accumulated only 530 total flight hours before final retirement in 1954. Other surviving Black Widows occupy museums across America. The Mid-Atlantic Air Museum in Reading, Pennsylvania, is restoring P-61B serial number 42 to 39445 to flying condition, a massive undertaking requiring thousands of hours and millions of dollars. If successful, it will be the only airworthy P-61 in the world. The aircraft will demonstrate for new generations what Macmillan's radar made possible, a heavy fighter that could hunt in total darkness and destroy targets that its crew couldn't see with their eyes. The story of the P-61 and the SCR-720 radar illustrates a fundamental truth about modern warfare. Technology can provide decisive advantages that overwhelm courage, skill, and numbers. German and Japanese bomber crews were not cowards. They were brave men flying dangerous missions. But bravery couldn't compensate for fighting an opponent who could see them when they were blind. Allied night fighter crews were not superhuman. They were well-trained professionals using tools that gave them overwhelming tactical advantage. The radar detected targets. The radar guided intercepts. The radar made darkness irrelevant. Edwin Macmillan solved a problem that defeated British engineers. He made helical scan and radar work when others had abandoned the concept. That solution, refined and productionized by Western Electric, installed in Northrop's massive twin-boom night fighter, created a weapon system that fundamentally altered the balance of night aerial warfare. Bombers that had operated with near impunity after dark suddenly faced interception by opponents they couldn't detect until cannon shells were already hitting them. The psychological impact was as important as the material destruction. Enemy crews who knew they could be attacked without warning flew differently, cautiously, less aggressively, or sometimes refused to fly at all. The technological race continued after World War II. Jets replaced propeller aircraft, missiles replaced cannons, sophisticated fire control systems replaced simple gun sights, but the fundamental concept remained unchanged. Detect the enemy before he detects you. Track him accurately through all conditions. Engage him decisively before he can respond. Macmillan's helical scan radar established this paradigm in 1941. 80-plus years later, the paradigm still governs aerial combat. The irony is that Macmillan's most immediately consequential wartime contribution, the innovation that killed hundreds of enemy airmen and helped establish Allied air superiority, is largely forgotten outside specialist circles. His Nobel Prize for creating neptunium is remembered. His leadership of Lawrence Berkeley Laboratory is documented. His development of the synchrotron particle accelerator is celebrated in physics textbooks, but the helical scan solution that made the SCR-720 effective rarely appears in his biographical summaries. Perhaps this is appropriate. Science awards prizes for discoveries that advance human knowledge. The Nobel Prize recognizes work that expands understanding of fundamental reality. Creating new elements revealed principles of nuclear physics. Designing better particle accelerators enabled experiments that tested quantum mechanics. These contributions were permanent additions to human knowledge, valuable regardless of political circumstances or military applications. Solving the helical scan problem, by contrast, was applied engineering under wartime pressure. It advanced technology rather than fundamental science. It killed people rather than enlightening humanity, and it solved a problem that, in peacetime, wouldn't have existed. Nobody needs radar to hunt bombers in darkness unless bombers are actually attacking in darkness. Macmillan's wartime work was brilliant engineering in service of military necessity. But it wasn't the kind of contribution that science traditionally honors with its highest awards. Yet for the Allied bomber crews who flew over Germany without being intercepted by radar-equipped German night fighters, and for the American ground troops who weren't attacked by Japanese bombers because P-61 Black Widows had destroyed them, Macmillan's radar work was far more immediately relevant than his Nobel Prize research. Technology that wins wars, that saves lives, that prevents enemy attacks, deserves recognition even if it doesn't advance fundamental understanding of reality. The mathematics of radar detection are straightforward. Power falls off with the fourth power of distance. Detection range depends on transmitted power, antenna gain, receiver sensitivity, target radar cross-section, and atmospheric conditions. Engineers can calculate theoretical performance from first principles. Macmillan didn't discover new physics. He solved engineering problems that prevented practical implementation of known principles. The helical scan mechanical system, the microwave feed to a rotating antenna, the display that allowed operators to interpret azimuth and elevation simultaneously. These were engineering challenges, not scientific discoveries. But wars are won by engineering as much as by science. The cavity magnetron was a scientific breakthrough, revealing new principles of microwave generation. But the SCR-720 was an engineering achievement, applying that breakthrough in ways that worked reliably in combat conditions. Both were necessary. Neither alone would have succeeded. Science provides tools. Engineering makes tools useful. Macmillan's contribution was making microwave radar useful for the specific application of night fighter interception. The Black Widow's combat record validates that achievement. 127 confirmed aerial victories, dozens more probable kills that couldn't be definitively confirmed. Countless missions where the mere presence of radar-equipped night fighters deterred enemy operations or forced enemy aircraft to abort missions rather than risk interception. The strategic impact extended beyond direct kills. Enemy bomber crews who knew they might be intercepted flew differently, less aggressively, with greater caution. They aborted missions when radar contact was detected. They refused to operate in areas where Allied night fighters were known to patrol. This deterrent effect multiplied the Black Widow's effectiveness beyond what the raw kill numbers suggest. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The final accounting of the P-61's contribution to Allied victory must acknowledge both the aircraft and the radar that made it effective. Northrop's engineers created an airframe that combined size, speed, and maneuverability in ways that contemporary critics thought impossible. The twin-boom configuration proved stable and controllable. The spoilers provided excellent roll response. The powerful engines gave performance that shocked pilots transitioning from smaller fighters. The heavy armament destroyed targets quickly and decisively. Every aspect of the aircraft's design served the mission of radar-guided night interception. But without Macmillan's radar, the airframe would have been merely an expensive curiosity, A large, well-armed aircraft that couldn't find targets in darkness was useless, regardless of its flight characteristics. The radar transformed the Black Widow from a capable airframe into an effective weapon system. The helical scan pattern ensured systematic coverage. The microwave frequency provided detection through ground clutter. The multiple displays allowed operators to search efficiently and track precisely. These radar capabilities, more than any aspect of the aircraft itself, made the Black Widow deadly. The story comes full circle to that March morning in 1941 over Connecticut, when Edwin Macmillan's radar detected that submarine from nearly 5 miles through overcast that blocked visual observation. He proved that the helical scan concept worked. The technology that seemed impossible to British engineers, feeding microwave energy to a spinning antenna without catastrophic losses, was not merely possible, but practical. Within months, production engineering would make it reliable. Within a year, operational squadrons would carry it into combat. Within 2 years, enemy bomber crews would be dying by the hundreds, shot down by fighters guided by radar they didn't know existed. The mathematics were unforgiving, the physics were immutable, the engineering was brilliant, and the strategic outcome was inevitable once the technology matured. Radar-equipped night fighters held decisive advantages over opponents who fought blind. The side that could see in darkness would dominate night combat. The side that developed better radar first would establish technological superiority that courage and skill couldn't overcome. Macmillan's helical scan solution, refined into the SCR-720, delivered that superiority to Allied forces and helped win the air war over both Europe and the Pacific. In the vast accounting of World War II, where millions died and entire nations mobilized their complete and industrial capacity for mutual destruction, one physicist's solution to an antenna feed problem might seem like a minor footnote. But technology compounds, small advantages accumulate, incremental improvements multiply. The helical scan radar that added perhaps 10% to detection reliability and search efficiency, deployed across hundreds of night fighters, flying thousands of sorties, shooting down hundreds of enemy aircraft, prevented thousands of Allied casualties, and destroyed strategic bombing capability that Axis powers depended on for nighttime operations. A block of copper, machined with 8 resonant cavities, generated microwave power that made short-wavelength radar possible. An antenna feed system that maintained efficiency through continuous rotation made helical scan practical. A massive black aircraft that nobody thought could maneuver provided the platform, and hundreds of bomber crews died without understanding what killed them, shot down by technology they couldn't detect and couldn't counter. That was Edwin Macmillan's contribution to winning World War II, not as famous as the Manhattan Project, not as celebrated as radar proximity fuses or Loran navigation, but for the specific mission of night interception, arguably as decisive as any single technology the Allies deployed. The blind hunt through darkness had taught both sides the same harsh lesson that Britain had learned in 1940. In modern warfare, the side that sees first usually wins, and the side that stops innovating dies. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today.